So last class was quite mathematically. That's because we introduced the concept of wave function, and then I went on to talk about wave function localization, delocalization, and all these things, right? But in your head, anytime somebody mentions a wave function, you should simply have a picture something like this, right? Basically, like a wave packet, mostly, right? And if your electron is, if you imagine an electron going from a gun to a screen, in your mind, you should visualize a wave packet that is going from the screen to the gun, from the gun to the screen, right? So let us think a little bit more about this before we proceed with the Schrodinger's equation solutions. So let us think of a physical experiment that we can visualize. There is an electron gun, okay, and there is a screen here. This is a phosphor screen. So I don't know if you know this, but we used to have this TV, right? It's like a glass, it's a it's a curved shape, and like an oscilloscope you have seen, right? So those kind of phosphor. So basically, an electron will hit it, and you'll see a bunch of light rays. So imagine this gun is shooting, right? It is shooting, and imagine there is a electric plates here. How will what would you always think about, right? So if I have a gun, if I maybe apply plus volt here, minus volt here, then the electrons, we think of it as they're going to go this way. They're going to light this part of the screen, right? Or if I apply a positive volt to the bottom plate, then they're going to come and do that. You're going to see a screen on the screen this way. But what is the size of that spot? Is it actually just a point? No, right? It has some physical extent. Comes from diffraction of electron waves. It's coming from the fact that electron waves can get diffracted. So what is the size of this hole from which electrons are coming? If I make the holes very small, then the spot will be larger. Okay. If I make the spot, make this hole very wide, then the spot will be very small. Why is that? That's again coming from position uncertainty, right? If I make that means in the y direction, I know the position of the electron to this accuracy, this much, right? So if I know the position to that much accuracy, then the momentum must have some uncertainty. Momentum in the y direction must have some uncertainty. So there is an uncertainty in the position in the y. So momentum in the y also must have some uncertainty. What do I mean by in the y direction? What that means is, if the electron is traveling this way, it has an x-directed momentum. It has a y component of momentum. This component we are reasonably sure about, but this component has uncertainty. So if I add the two momentum up, the sum will be either it will be here or it will be here. It will have a range of values, right? So position momentum uncertainty in the y direction corresponds to position uncertainty on the screen, where it will hit the screen. And the more I confine, the wider this spread. So the electron is coming in a very small hole. Have the spot on the screen will be quite big. Okay. And when for that you can even not even have this, right? You don't even have this electric plate. Then I'll have a screen on, it will be like this, right? It will be a patch on the screen. How wide is the patch? It depends on what is the size of the hole, right? Is there a Does this make sense if the electron was a complete particle? No, it doesn't make any sense if the electron was a complete particle, right? Because this diffraction, the size of the hole, if the size of the hole is much smaller than the particle won't come out. If it's quite big, if it's the moment it becomes larger than the hole, the particle will come out. The size of the hole of the particle, doesn't change the momentum in the y direction. So, this is again a property of the wave property, right? So now that
Excuse me.
yes.
Sir, like I don't know if this is a problem with me only, but your voice isn't clear. Like it's a lot of disturbances coming in between. So like I would request if anyone else is having any problem with the same thing.
Yes, sir, same thing.
Is it better now?
Yes, sir,
It's
much better.
better.
Okay, do remind me if this is the case. So, okay, and you may be wondering, look, I am dealing with electronic devices. Why does this thing matter? It matters because I want you to, whenever you think of electronic devices, I want you to have a better conception of the electron, right? Anytime you think of electron, you're always going to be thinking in terms of ball, right? Little ball that is moving. You have to get away from that. That is why I'm showing you many, and these experiments can be conducted in daily life. You can visualize the quantum nature of the electron by these experiments, right? So that is the diffraction of the electron. But there is an even more interesting consequence here that you may not have realized. And let us go into that. Let's say there's electron gun here, okay? And there is a screen here. Now we do some interesting experiments. There is a size of the electron, this hole, right? It is reasonably small. So there is a spread of velocities. So on the screen, I'll have a dot, and it's going to be more bright at the center. It's going to be dimmer but it's going to be like a ring. It's going to look like if it's going to look like a ring like this, right? It's going to look like a diffuse ring on the screen, but brightest at the center, getting duller and duller as it goes outside. The size of this thing on the screen will depend on is inversely proportional to the size of the hole from which the electron is coming. Everybody got that, right? Great. So that is the first experiment. Yes, we've finished that. Next, we're going to do something a little bit surprising, right? So yeah, maybe the mathematics won't convey this to you, right? So let us say now we're going to put a hole. We're going to put a second hole, right? We're going to put a hole like that. We shouldn't make the hole too large. It should be reasonably small only. So I'm going to put a hole like that. Okay. Now what will happen? Now you won't be surprised, right? So now if I see what is going to happen on the screen, I told you electrons have different electrons go in different trajectories in a way. So some electrons will fall on the wall. They won't come back. But whichever electron has the correct kind of direction, it will go and hit the screen. It will go and hit the screen somewhere here. Right? No surprise. Okay. Next, we're going to put, so imagine this is a door. Okay. There's a trap door like this. Now my window has another trap door. My screen has another trap door. Okay. I'm going to open this guy. I'm going to open the second trap door like this, the lower trap door. So now what will happen? Now I'll draw the screen again. So now this is when the top is open. This is when the bottom is open. It's going to come here, right? So you're going to have a spot here. Okay. Now let's do the interesting experiment. Let's open both. Now we open both. Okay. And right. So before telling you the story of actually what happens, what is observed on the screen, let us think about it, right? So I'm going to eliminate, yeah, maybe I'll keep it as no problem, right? So an electron, could either go through the top one or it could go through the bottom one, right? So equal probability. And so what do we expect to see on the screen? We expect to see on the screen something like this, where if the top was open, I would have seen, maybe let me do this slowly. If the top was open, I would have seen this kind of thing, top. If the bottom hole was open, I would have seen this kind of a thing. Now, yeah, this is the bottom one. Now, when both are open, what do you guess? It'll look something like that, right? That's what we guess. This is what it would look like if the electron was actually classical. So classical, top plus bottom, both of them are open. But actuality, the pattern looks very different. Actual pattern looks something completely out of the ordinary. It actually looks like this. Right? So when both doors are open, turns out the spot will come in the center. And there'll be other extra spots a little bit outside as well, something like that. So this is a classic interference pattern. Interference pattern. So you cannot interpret this at all in terms of a particle, because the particle cannot go, one particle cannot go through both holes at the same time and then interfere with itself, right? So that is not possible. So the only way to visualize this is if you visualize the electron as a wave function, e to the power j omega t minus kx. Then the probability wave is really going through both of the hole at the same time. And once it goes, so mathematically, how do we think about this? So if there is a screen here, the electron, from the electron gun, we can imagine that a plane wave is going like this. This is the plane electron wave. It has a wavelength, it has frequency, everything. Once it hits the screen, this plane electron wave function converts into a circular wave function like this. It is these two secondary waves now that actually interfere on the screen to give you a interference pattern like this, right? So this is how you should visualize the electron wave. Now there is a twist to this experiment. If I put an electron detector apparatus on one of the holes, okay, why am I doing that? I'm saying, okay, look, I don't believe your wave picture. I want to try to find out which hole it is going through. So I'm going to put the electron detector. If the electron detector registers a click, right? I put one on this guy also. So either this guy registers a click or this guy registers a click. I'll have to, either one of them registers a click. But when I put the detector, then I get this pattern again. Okay. So that is a surprising thing. Why that happens is because the presence of the detector disturbs the wave function. It disturbs the wave function, and so interference cannot happen if you have disturbed the wave function. So the moment a click is registered here, the wave function dies, and this portion of the wave that dies. It's not there anymore. All the wave function from a plane wave, it is now compressed into a small wave packet, basically. Okay, that is what is happening. Right. So I hope you are now beginning to visualize the electron in all its wavy glory, right? So I hope you're doing that. Great. So I just want to add this because in the book, there is a problem of this, right? And mathematically, how do we solve it? We write equations, right? What is the equation for this secondary wavelet? It is j omega t minus k into r, where r is the there is a 1 by, there is a r by r square here also, right? We, by r factor is there, we don't worry about that. K into r, right? So let's say this is your hole, this is your second hole, this is the screen, this is the 0 on the screen, this distance is d. Now, how do we find out this interference pattern? Let us say I want to know the interference pattern at any particular point on this at a distance of x from the origin. I'm going to draw the lines. This is how the top secondary wavelet travels this distance, bottom secondary wavelet travels this distance. And so at this point, the wave is a into e to the power minus j k r, right? That is the expression. Here, both of these are in phase at that point. So I have to add basically top wave and the bottom wave, e to the power minus j k r1 r2, where r1 is this distance, r2 is this distance. We have to add these two things. Then at some places, what will happen? This will sum to 0, and that location you will never detect the electron. Some locations, what will happen? This will give you 2 times, basically 2 times probability. So okay, that is the problem that is given in the textbook, and this is how we solve it. We have a you can look at it in the textbook how to do this. So what is R1 and R2? What is R1? To calculate R1, it is basically d by 2. This is distance. Here is d by 2, right? This distance is d by 2. This distance is x. So we'll draw this triangle. And so this particular dish is x minus d by 2. And this is the length L of distance to the screen and the holes. So R1 is basically x minus d by 2 squared plus L squared square root of. And R2 is basically x plus d by 2 whole squared plus L squared. And so when you try to add this, we can write it as e to the power minus j k r1 plus e to the power minus j k r2 is there. Now, this kind of a sum, I can extract the k r1 out and say 1 plus e to the power minus j k r2 minus r1. And then we have to take the mod squared of this, right? This first term is going to give 1 anyway. Second term is going to, this at most this can go plus or minus 1, right? It's e to the power minus j something. Wherever it's going plus, I get 2. Wherever it's going minus 1, I'm going to get cancellation. That's it. So that is how you do it. So basically, what is k of the electron? K is lambda is h by p. So p is h by lambda, or p is h bar k. So k is nothing but p by h bar, whatever the momentum of the electron is. So k is known. And this we can simplify, right? So normally what will happen is the length of the screen, the distance between the screen and the holes will be much larger than distance d between the holes. So your interference pattern, will only exist for very small distance around the screen, right? So we can make some simplifications. We know that this first number is going to be much smaller than the second number. And so how do we do that? So we will basically divide by L square and take L outside. It's going to be 1 plus x minus d by 2 divided by L square root of that. And that can be written by the binomial theorem because the second number is quite small. That's 1 plus 1 half of x minus d by 2 by L. So if I take the difference between the two, so I will then, you see I want k r1 minus r2. After applying this simplification, if I take the difference, then the difference will be x minus d by 2, other one will be x plus d by 2. So x will go off also. Everything you can express in terms of L and D. Okay. So I'll show you where this has been done in the book, so you can actually have a look at that. So this is our textbook. In the very first chapter in the textbook, there's a chapter called the quantum particle, what I call the wavy particle, right? So he's going to talk to you about that. And the very first thing he does is he's going to introduce you to this idea of, see, this is your hole, basically single slit, right? It comes to single slit and you have diffraction, right? So then he's going to introduce two slits here. You can see two slits. And classically, we predict that there should be no interference, right? But when we have wavy particle, I'll have an interference fringe. So what is the distance between the interference fringes and so on? That is the calculation that he will do here. He's doing that calculation here. Okay, this is the so-called double slit experiment. You see exactly what I've done, right? R1, R2, and so on. And finally, we end up by saying that the spacing between the bright lines is given by L into lambda by S, where L is the distance to the screen, S is the what D we use, not distance between the holes, and lambda is the wavelength of the electron, which is given by P. P is equal to h by lambda, right? So that lambda is h by P basically. The higher your momentum, smaller the lambda. So we can see this, the smaller the lambda, ideally your hole size, this S must be reasonably comparable to lambda. If it is not comparable, if S is much larger than lambda, then this Y will become 0, almost close to 0. That means you will not be able to resolve the fringes clearly. So to see the fringes clearly, S must be quite small. It must be comparable to the wavelength of the electron. So regularly, every day, you won't see this. So in a way, even you, right, you and I, we are also quantum particles. So for example, I always take Pankaj as an example. Pankaj is really a quantum particle in a way. So if we can design the doors in but what happens is his de Broglie wavelength, this lambda, is very, very small. It is 10 to the power minus, some 30 odd meters, right? Very small. So you have to position the holes at that distance. So if you do that, that distance, then if you send Prankush to that door, to these doors, then Prankush will interfere with himself basically, essentially, and on the other side of the screen, you may be able to find multiple Prankushes, for example. But this doesn't happen in daily life, right? Why? Because the de Broglie wavelength for me and any object, even for an object as high as a stone or something like that, there also the de Broglie wavelength is very small. So small that these fringes in daily life are not observable at all. However, when you go to the size of an electron, then this effect start to dominate, right? So any mass also is basically a quantum particle. That's why. So don't assume that you are not quantum entities. You are also quantum entities. The reason is that your quantumness is too small to observe. Right? So that's why it appears to us illusion that we live in a classical world where particles have defined positions and they don't. Right? So for example, I'm sitting on this sofa right now. If you say, oh, sir, but you are sitting idle, you don't have any position, you have your positions also known, your velocity is 0, you're not doing anything. How is this resolved? It is resolved because actually my position has some uncertainty. Even my momentum also has some uncertainty. In a way, I'm really moving around, right? I'm oscillating, but I'm oscillating so minutely But some people have big stomachs, they probably oscillate visibly. If I'm oscillating so minutely that you will not perceive it. Okay. All right. So yeah, don't think that we are completely different. We are exactly this. We are just a bunch of electrons. We have the same property, except that our de Broglie wavelengths are much smaller. Okay. This is an interpretation of the double slit experiments. Then the book talks about the wave function. I've already done this. I want to show you also, frequency domain K. This let me talk a little bit about this. So
Sir.
this is yes.
Sir, sorry for interrupting. Sir, I actually have a question.
Mhm.
So, like when two waves are interfering, so we always know that it's a central maxima, right? And the reason that is given in most of the books is like that these two waves, when they're interfering, they have the same phase because they're traveling the same distance.
Mhm.
So there is a bright central maxima. But
Right.
sir, I always wondered that suppose even if two waves are interfering and they have the same phase difference, but it may so happen that the two waves have zero amplitude and then they are interfering at that point. So
Yeah.
how is always bright?
I got it. Yeah. So even if they have zero amplitude at the start, then also they will get zero here, right? Is that what you're saying?
Yes, sir.
But if I have zero here, I will not see any bright spots on the screen at all.
But suppose, sir, I'm changing the distance such that when the waves are reaching that point, two waves are reaching such that they have zero amplitude at that point.
Okay. Right. So the amplitude, I got that question. So this is a wave, right? So this is a circular wave. This amplitude never goes to zero anywhere. Okay. So see, you are confusing. If I have a wave, so this is my wave, right? What is the amplitude of this wave? It is always one throughout. The phase is the quantity that is going plus and minus. Okay. So here also, when I have two waves that interfere at any particular point, the amplitude of this part is never going to be zero. If the amplitude is zero on both sides, then I never see any pattern at all. I'll not see a bright, dark. No, I'll see black throughout. That means there is no wave only. But if the amplitude is not going to be zero, but the phase will be zero. So one wave. Yeah, let me show you that. Right. So this is one of your wave. Second wave is coming like this. If for some person here is looking at the wave as a function of time, it's coming like this. But the second wave is coming in, it's like this. See, they're out of phase, right? So this guy will never observe anything. But the guy is sitting here. For him, what will happen? For him, the one wave will come like this. The other wave will also be like this only. Okay, so you need to distinguish between phase and amplitude. Amplitude of a wave doesn't change. Sine wave, its amplitude always remains the same. But at different positions, its phase will change. Is that clear?
Yes, so sir, suppose the person who is sitting in the center, if he is seeing that phase 180, then won't he find zero? Like
no, right? Because see, at one point, at this instant of time, so this is a function of time. Okay. See, this is the person who's sitting at the center. He's observing as a function of time. As a function of time, at this instant, he'll see bright. Here there'll be zero. Here he'll see bright again. Here he'll see zero, right? But the guy who's sitting here, at all time, he'll see zero only. This guy will see bright zero, bright zero, bright zero, like this. Do you see that? You are confusing time and distance. Is that clear now?
Yes, sir. Yes, sir.
As a function of time, the guy at the center, it will go up and down, up and down. So standing wave, it will go up and down, up and down, up and down. But the guy here, always zero. That is the difference. Do you see the difference now?
Yes, sir. Yes, sir.
This is clear? Okay, great, right? Yeah.
Thank you, sir.
Yeah, thank you. Okay, so we are going to now go into frequency descriptions. Remember, in electrical engineering, if I have a signal, if I have signal as a function of time, I can take this to the Fourier domain, omega domain, right? In the same way, if I have a function that is a function of distance, I can take it to the k space. Okay. So the k space is the moment is like the Fourier transform of the space, basically. So k is nothing but a spatial frequency. It's called a spatial frequency. So a function of f is a function of time, right? So let me write it mathematically. If f is a function of time, I can do a Fourier transform on it, and I'm going to get f of omega, right? In the same way, if I have f as a function of space, if I do a Fourier transform on it, I get something that is a function of k. Okay, so let us visualize some of these things. So imagine, let's do in Fourier domain and time function first. Imagine I have a function that is a pure sinusoid in time. So it goes from minus infinity to plus infinity. What is the frequency representation of this? It's basically delta function at omega and minus omega, right? Yes, I hope everybody knows this, right? Everybody remembers this. So similarly, so this is completely delocalized in time, right? If something is delocalized in time, then it is entirely localized in. Just give me a second. Hello? Sorry about that. If something is delocalized in time, then it is completely localized in energy. Okay. And equivalently, if something is delocalized in space, then it will be localized in, it will have a very definite k. Okay, so I hope this concept is now clear to you, right? So this is a delocalized wave packet. Now imagine a wave packet that is somewhat localized like this. Maybe I'll draw it correctly. I'm just drawing envelope, right? So this one is a function of space. Because it doesn't have a definite k, right? If I take the Fourier transform of this, I'm going to get not a delta function, but a proper Fourier transform. Okay. So, and now if I ask you what is its momentum, you say, I don't know. It doesn't have a proper value, right? Can be anything like this. Same idea holds if I have a wave packet in time. If you take its Fourier transform, then you again get a Gaussian, right? So, so there's no definite energy. So that is the concept that is being talked about here, frequency domain and k description of waves. Okay. This is for you to revise. So if I give you now a wave function psi as a function of x and time, you can apply Fourier transform to it. And essentially you're going to end up with some wave function a that is going to be a function of k and omega, right? Right. Usually people don't do for both dimensions. Remember I said we have time independent wave functions, right? And for time independent wave function, if I apply Fourier transform, I'm going to get something that is a function of k. And you can do it. So for example, if I have e to the power minus j kx as the wave function, what is its Fourier transform? it is nothing but delta k minus k minus k naught, right? This is k naught, yeah, k minus k naught. Everything that you have done with Fourier transforms holds here. Okay. Yeah, and he is giving you actual relations where we do that. Now he will talk about wave particle waves and uncertainty. So if I have a Gaussian wave packet, don't worry, there is a homework problem coming up. We're going to do this in depth. I just wanted to introduce it to you over here. If I have a Gaussian wave packet, it's a Gaussian wave packet. And if I take the inverse Fourier transform of that, not in Fourier transform of that, I get the wave function description in K space. And that is also a Gaussian wave, Gaussian in K as well. But there is a relationship. If I have a, see, it is sigma here coming in the denominator, here sigma will come in the numerator. So the wider the particle spread in space, in real space, the narrower it's spread in the K space, and vice versa. So we're going to, using this idea of, is how you derive the uncertainty principle mathematically. We're going to do that, right? There is one thing that I did not introduce last time. I'm going to introduce that to you now. That is called the expectation, expected value, right? And this is a probability concept. So let me explain this. Say I have a dice. Okay. Dice 1, 2, 3, I have a dice. So I'll tell you, okay, if one lands, I'm going to give you 10 rupees, $10. Let's make it fun. If 2 lands, I'll give you $20. If 3 lands, I'll give you $30. If 4 lands, however, you're going to give me $20. If 5 lands, going to give me $3. If 6 lands, we don't do anything, right? Zero exchange. Now, if I ask you, okay, will you play this game? Yeah, you would love to play this game, right? Because I'm losing my shirt here. In a very few rounds, you'll win. So then I will ask you, what is your expected win per round, right? Then how do you do it? You will basically have to multiply the probability of each event. So you'll have to say, okay, 1/6 of the time I'm going to make $10. 1/6 of the time I'm going to make $20. 1/6 of the time I'm going to make $30. 1/6 of the time I'm going to lose $20. Plus 1/6 of the time I'm going to win $3. Something like that, right? And when you sum this up, you're going to get some value at the end of the day. If that is positive, that means this is a positive, good move for you. So these kind of, so if that is the case, then it's called positive EV plus EV game, right? So now same idea, my wave psi x t is telling me the probability of locating the electron at any location x and t. So now if I ask you, let us say you do this experiment, right? Repeat this experiment, take the same wave function, this prepared in this state, keep repeating, going different places, different times, finding out the probability, finding the electron and so on. I will ask you, what is the expected value, expected position for this particle? How do I do that? To do that, I'll have to do integrate over time and space, or all time and space, psi star x comma t multiplied by x multiplied by psi x t dx. This is called the expectation value of x. So sometimes, for your wave packet, imagine a wave packet like this. And this is the exact origin. What is the expected value of this position? It's the origin, right? Right. So this is the expectation value x. Okay. Now, what is that is the average position. What is the standard deviation of this? How do we calculate the standard deviation? Right? Standard deviation is basically telling you how far away the particle can be found. That is given by expectation value of x minus expectation value of x. This is called delta x. This is your standard deviation. Okay, think about it very carefully. So, what does that mean? That means yes, on an average, sometimes you may find the electron at +5, sometimes you may find it at -5, but on an average, if you add up all the things, you get 0. That means it's wandering in and around the origin. But is that information enough? Not really, right? I could be wandering in and around the origin, but how far I wander, that is also important. That is coming from the standard deviation. And the larger the standard deviation, that means it's very wide, right? Okay, so I'll tell you an example, right? So let us say you are running a business, and today you make $10, tomorrow you lose $5, right? On an average, you are making 0 money. I'm sorry, maybe I'll give, maybe let's say you are making $100. Okay, on an average. But does that mean, today if I come to you and say, "Arey yaar, aaj ka paisa de do," will you be able to give me $100? Not really. It depends on the standard deviation, right? If the standard deviation is less, that's good for your mental safety, right? So if the standard deviation is plus or minus $1, that's very good, because रोज का आपका खाना वाना बन जाएगा. एक दिन 101 आएगा, एक दिन 99 आएगा, बिल्कुल no problem. But imagine a business that has 100 on average, or maybe I'll give you another guy. This is guy A. Another guy is there. He is making very nice. Okay, he is making $300 on average, but his standard deviation is $1,000. Who do you prefer to be, this guy or this guy? Most people prefer to be this guy. Okay, because यहाँ देखो इतना बहुत fight है, right? Today he's going to make $1,300. Very good day. Tomorrow, $1,300 minus $700 loss. Next day also minus $700 loss. Very tough job, right? So if you're doing day trading, this is the kind of guy you'll be. If you're doing some boring job like me, then ये भी नहीं है. 100 monthly होता रहेगा. 0 standard deviation job अपना है. ठीक है? Okay. Right. So this is the salaried job, right? $100 is there. Zero standard deviation. But auto चला रहा है, कोई trading कर रहा है, उसका ऐसा होगा. So I hope you realize the difference. So wave function also like that only. So some wave functions are, although their average position is 0, they could have divergence, right? And this is your uncertainty. When I say position uncertainty, this is exactly what I mean. Doesn't have to do anything to do with the mean value. It's a standard deviation. So what is the expected value of the momentum? Well, how do we do that? We write an expression for that. I write psi star, psi conjugate, complex conjugate of, then momentum operator. What is momentum operator? We know that, right? It is I h bar d by dx. And I do this psi xt dx. This is going to give me the expected value of the momentum. Again, some particles will have 0 momentum. That means they're not really moving, but their standard deviation of the momentum is p minus expected value of p. This is delta p. This may not be 0. Now, delta x into delta p is always greater than or equal to h, right? This is my h bar by 2 pi. This is your uncertainty principle. And to prove that is the proof here. So we're going to prove that. You're going to prove that. Okay. By taking the example of a Gaussian particle, you're going to prove that. You're going to prove the uncertainty relationship. This is going to be in the homework. Yeah, this is going to be in the homework. Okay. All right. So I hope you can, this is good for you to manipulate the wave function mathematically. now that you have understood the concept of what is a wave function and so on, this is going to be a good drill to do, okay, to really ensure that your concepts are correct, right? Once we understand it in language, we try to understand it in mathematics. See if we can actually solve problems. And that is where, if our understanding is a little bit shaky, is we'll know there, right? So this is your expectation value of position, x. Then the denominator, wave function is normalized, denominator is 0, right? So this is how they do x. See, this is how they do, like I showed you, right? They have a normalization factor. If it's normalized already, then you don't need the denominator. Okay. There's a bracket notation. So every time, I don't want to write this psi star multiplied by x, psi, all this, right? So very simply, you can, this integral that is there, psi star xt into whatever operator you want, multiplied by psi xt dx. This is the expectation value of the p operator, right? I can write this as psi p at psi, not p, psi, like this. So this triangle tells me, you are integrating. It tells me what is the order of integration. So if I do something like that, that means it is psi star only. Okay. Yeah. So this is called the bracket notation. Bracket, right? Bracket ko split karke, it's a bracket notation. Okay. So what in this notation, what is the expectation value of x? There's nothing but psi x psi divided by psi star psi. Okay. You don't have to add a conjugate in the bracket notation. It's understood. If it's coming on the left, it's a bracket, it's a bra, not the ket. Then you will know that, if I write like this, that means it's a psi star on the left hand side. Okay. This notation. What is the momentum expectation of the momentum operator? The psi at momentum operator multiplied by psi divided by psi star psi. What is the delta x? Delta x is nothing but expectation value of x minus expectation value of x, right? So this is hashtag x minus expectation value of x into psi divided by like this. Okay, so this is a simplified notation. You can use it from now on. I hope you understand what that is, right? It's just this integral only. That's it. So that is what is introduced next in terms of the bracket notation. Then we have the Parseval's theorem. It helps you to normalize the wave function. I'll not deal with this. We don't really need it at all. So I'll leave it actually. I'll also not talk about what is a commutator and so on. It's really a little bit more into mathematics of quantum mechanics. We don't really need that, right? So we'll eliminate that. Okay. Then we come to momentum and energy. And I've already introduced all of this to you. What is the P is equal to HK, E is H bar omega, that part. Then you have the uncertainty principle, uncertainty in time and energy also I've introduced. Application of uncertainty principle, no worries, we've done that. Finally, he comes to Schrodinger's equation, which is what we have already done. Then he is summarizing all the different operators. We know this also, right? So we have the position operator is simply x. We have the wave number operator. Momentum operator is nothing but h bar times the wave number operator. Angular frequency operator, yes, I d by dt. Energy operator, I h bar d by dt. That's it, right? Momentum operator comes from wave number operator. Hamiltonian is basically addition of potential energy operator and kinetic energy operator. So Schrodinger equation, I think, says the Hamiltonian of psi is equal to energy of psi. This is the Schrodinger's equation. Then he talks about time independent Schrodinger's equation. I've already done that as well for you, right? So this is just to tell you that whatever I have covered, if you want to revise those concepts, please go to the textbook and you can revise those concepts. I covered in slightly different way, different order, based on my own lecture style or whatever, but it is all there for you to revise should you feel the need for it. Great. So now we come back to the Schrodinger's equation, time independent Schrodinger's equation. Remember what we did here. We had the Schrodinger's equation. And in general, this is true for any wave function of a function of space and time. Well, in general, it's even harder. You can have all four coordinates, right? X, Y, Z, and T. This is equal to some scalar multiple of E times X comma T. This is Schrodinger's equation. Okay. Where E is also an operator, H is also an operator. What we said is, assume that the wave function can be split into a time part and a space part. Now, in general, this is not possible. Why? Because this actually translates into minus I H. No, not minus I. Minus H bar squared by 2m plus V, which is a function of X comma T. I'm only talking about one dimension for now, but you can generalize to, sorry, I forgot the division operator. Sorry, the derivative part, d square by dx square. If it's three-dimensional space, this will replace by a gradient operator, vectors and gradient. More complicated, so we'll not deal with that yet. Plus u, which is a function of x and t, multiplied by psi x comma t. This is I h bar t by dt of psi x comma t. This is my general equation. If this potential is not time independent, or that cannot be broken down into a factor like this, then forget it. You cannot, the wave function will not be like this. Okay. So the only condition in which this is possible is if this potential is just a function, it's time invariant. Potential is time invariant, then we can replace this by separation. And when we do that, we find out that ultimately all separable wave functions are of the following form: psi x into e to the power I e by h bar t, and phi x satisfies the equation h squared by 2m d square by dx squared plus u of x phi of x is equal to e times phi of x. This e and whatever e appears here, they are the same. Okay, they should be the same. In general, if I have this equation, it will have multiple possible solutions. Solution may not be only one solution, maybe multiple solutions. Each solution is characterized by one eigenvalue. Maybe this one is eigenvalue E1, E2, E3, and so on. So this will be phi1 of x, phi2 of x, different eigenvectors, eigenvalues, eigenvectors. In some situations, this E1, E2, this can be countably infinite. In some situations, it can be uncountably infinite. It can be continuous spectrum. All variations are there, as we will see later on. Okay, so these are independent solutions of this equation. Remember, when we know about theory of differential equations, right? If there is independent solutions to an equation, then the most general solution is going to be a linear combination of the individual possible solutions. Using that idea, I can now write my full equation in the following way. It is phi1x e to the power I h bar, no, not h bar, I e1 by h bar t multiplied by a constant a1 plus a2 phi 2x e to the power I e2 by h bar t plus a3 times whatever, right? The most general solution for a time independent problem is a linear combination of each of the energy eigenstates. These are called energy eigenstates. Phi1, phi2 are energy eigenstates. Okay, this is the most general solution, right? And all interesting effects of quantum mechanics, like superposition, state preparation, all that idea actually comes from this thing. Okay, because this A1 and A2 are in general complex numbers. Okay, so you can have all kinds of very interesting things happening with this, but I hope you understand why this is the more general solution, right? We'll explore all the superposition part later on, but I hope you see what is a more general solution. Okay, we'll go to the physics of it and then it will become more clear. Now it's a little bit only on the mathematical side, right? So now this is I've covered the general mathematical theory. Now let us try to build intuition. How we build intuition? We basically take different possible scenarios for the potential energy, and based on that we'll see how the solution of this differential equation looks like, what are the eigen energies, what are the eigenvectors, and so on. And the simplest of the time independent Schrodinger's equation is when u of x is 0, no potential, free space, completely in free space. So this multiplied by phi of x is equal to E times phi of x. We want to solve this particular problem. Remember how we solve ordinary differential equations, this d by d that we have to replace by capital D, right? So the h squared 2m capital D squared of phi of x is equal to E times phi of x. And I'm going to write it in this way now. D squared phi of x is 2me by h bar squared into phi of x. I can write that as t square plus 2me by h bar squared times phi of x is 0. Remember, what are the solutions? I have to first solve this equation, right? So this gives me d is equal to plus or minus root 2me by h bar squared. J. Why? Because minus, right? It's a negative number. So plus or minus j root of 2me by h bar square. If that's the case, then I can say that my final solution is a into e to the power plus j 2me by h bar squared root 2 h bar squared times x plus d into e to the power minus j root of 2me by h bar squared x. I write it like this. Let me call this number k h bar squared. And you will notice that the units of k will be 1 by x, 1 by space. So it's nothing but the wave vector. Okay, that's all it is. So I can write that phi of x is nothing but A into e to the power jkx plus b into e to the power minus jkx. Now both of these have the same energy. So actually I can write the actual wave function is a into e to the power j omega t plus kx plus b e to the power j omega t minus kx. So this is nothing but a backward and forward traveling plane waves. So what have we discovered? If there is, if I have an empty universe, there's nothing in the universe, and I have an electron which has a certain value of energy, and immediately I know that I cannot, this energy must be entirely kinetic, right? Because we are considering the case where ux is 0. We are considering the case where potential energy is 0. So I have an electron which has a certain kinetic energy E. P squared by 2m is E. So P is nothing but root 2me by E, right? 2me by, so it has a certain kinetic energy E. Then I know that the electron is actually delocalized. In an empty universe, an electron of certain energy is found really everywhere. It's not localized at all. Why is it not localized? Because there's nothing to localize it. I need some other charge to kind of capture it and so on, right? This is completely free electron. If there was an empty part of the universe, you let an electron go, this is what will happen to it. It will spread everywhere, right? And there will be two components. One component will be, it will be a sum of a backward traveling component and a forward traveling component. And plane wave. So it is essentially, it's going to be a standing wave. Okay, that's what it's going to be. It's going to be a standing wave, and its wavelength is going to be, its frequency is going to be omega given by E by h bar. And what is its wavelength going to be? Wavelength is going to be h bar times k, which is 2me by h bar squared. So it's going to be root 2me. Is going to be its root 2me is going to be its momentum. This is its momentum. Okay. So yeah, again, both are functions of E, basically, right? So other things you discover here, if the particle is very massive, if it has a very high mass, then P is also very high, right? So again, not surprising. Right, so that's it. So free electron is very simple. It's the simplest possible state. Free electron will simply be a infinitely delocalized wave. This is surprising, right? Because in our mind, we say, okay, if there is a universe, if I just let one electron go there, it's just going to be a small ball that's going around. No, not really. It's going to spread out everywhere. And it's going to obey this kind of a law. This is called a plane wave function, right? Okay. This is the easiest solution, right? So nothing very surprising here. Now, question is, okay, this is the eigen state, right? This is the energy eigen state. What are the possible eigenvalues? There is no constraint on eigenvalues at all, because any value of E you give me, I have a physical wave function, no problem. So in general, E can be anywhere. So you can go from, it cannot be negative though. I cannot have a negative energy. Why not? I cannot have a negative energy because if I have a negative energy, then this root 2me by will also give me j times something. That j and this j will cancel, and it will give me my eigenvector will be of the form e to the power minus kappa times x, which means it's going to be delocalized. Okay, it's going to be localized. But we know it's a free electron, there's no potential, so this is not possible. They cannot be localized because there's no potential to localize it. Hence, E cannot be negative. So for a completely free electron in an open universe, E can go anywhere from 0 to infinity. including zero. Okay, including zero. What happens if it is zero? That means its momentum is going to be zero also. P is root 2 me, right? Momentum is also zero. That is the case where wave vector is zero. Very long wavelength, basically. That's what it is. Okay. Ideally, like infinite wavelength in the way. So this is the only situation in which a quantum particle can have energy zero. I know Prankush asked the last time, right? Any bound electron, if your quantum particle is bound, it cannot not have a zero energy. You'll discover that the wave function itself will go to zero. If that is the case. Only in the case where it is fully delocalized, spread everywhere through the universe, then it can have energy zero. Okay. So that's that. So what are the possible eigenstates? Eigen values, energy eigenvalues, 0 from infinity, all values included. Continuous eigenspectrum is what we call it. Any value is possible. Shouldn't surprise us, right? If there's a electron in free space, nothing is bounding it, nothing is stopping it, nothing can have any energy, no problem, right? What are its eigenvalues? It's again e to the power j kx, forward and backward traveling plane waves. That's the eigenstate. Those are the eigenwave functions, eigenenergies. Done. Very simple. Great. Now let's go on to doing something more interesting. Clearly, u of x is 0 is not very interesting, right? So next, I'm going to do some very strange wave function. I'm going to do something called an infinite potential well. What I do in an infinite potential well is the following. I'm going to say that u of x is infinity, infinite potential. U of x is infinity over most of x, except between 0 and d. Okay, so let me write it mathematically. So ux is infinity for x less than 0, less than or equal to 0. U of x is infinity for x larger than d. U of x is 0 for x between 0 and d. So physically, what is this kind of a situation? It's basically like a kuwa hota na, it's a well basically. It's a kuwa hota hai bada wala. So you are basically gone inside the well. Okay, you're standing inside the well. What is the meaning of an infinite potential well? That means you need infinite energy really to climb up. That means, you hopeless situation, right? You're dead. You're done. So that is exactly what it is. We are subjecting to the electron to this cruelty, right? We're putting it in an infinite well and seeing what happens. So we know that electron can never get infinite energy. That's not possible. That means there is no way that it will ever be found anywhere other than the well region. So even without doing any quantum mechanics, any Schrodinger, Bodinger, whatever, I can immediately say that psi of x, phi of x, the wave function. First of all, we say it is time separable. Why? Because this doesn't have any time dependence, right? So immediately I know that the potential doesn't have any time dependence. So my equation is separable. So I'm going to solve actually the time independent Schrodinger's equation. And so I'm going to write only phi x from that point onwards. I know that phi x, it's going to be some function. That's what we're going to find out. But even before doing any of that, just by the physics, I can say that it's going to be 0 for x less than 0. Okay. Why? Because it cannot cross, right? It's also going to be 0 for x larger than d. Less than 0, larger than d. Okay. In fact, I have to say or equal to. Exactly at 0 also, the well already starts. So, your wave function has to go to 0 there. If it is any other value, there is a problem because the wave function will become discontinuous. That's not allowed. So I have to actually say x less than or equal to 0. And I have to say x is larger than or equal to d. Wave function is 0. Great. Okay. Within this region now, we need to find out, okay, what happens for this region? What happens? Well, let's do it, right? So we'll say it satisfies whatever this is, it's going to satisfy my Schrodinger's equation, square by 2m plus u of x. But within this region, u of x is 0. Phi of x is e times phi of x. Great, right? So this is nothing but minus h squared by 2m d squared by dx squared. Phi of x is equal to e of x, phi of x. Where have we seen this equation? We just solved it, right? We just solved this equation earlier. So I can write that the solution must be of the form a into e to the power minus jkx plus b into e to the power plus jkx, where k is root of 2me by h bar squared. We don't know exactly now what values of energy are allowed yet. Okay, we know that within inside this region it should satisfy this equation, but the a and b are right now undetermined constants, but we have to determine them, right? How do we determine them? We have to apply boundary conditions. What are the boundary conditions? This is the boundary condition. At 0 the wave function has to go to 0. That's it. That's a boundary condition, right? So, and beyond that also it should go to 0, but at least at that it should go to 0. So we just substitute at x equal to 0, this must go to 0, implies that a into e to the power minus jkx is 1, right? So nothing but a plus b has to be 0. And we know that it should also go to 0 at x equal to d. Yeah, somebody asking a question here. Is the voice still not clear? You are having problems still?
No,
Sir,
sir.
it's
I have
clear now.
sent the message 1 hour earlier actually.
पहले का था ना, अभी तो प्रॉब्लम नहीं है ना फिर?
नहीं, अभी तो बहुत सही है.
Okay, thank you. Great. Yeah. So then we say a into e to the power minus jk x equal to d, jkd, plus b into e to the power plus jkd should be 0. Right? You can impose some other kind of conditions also. You can say that, we can impose a condition on its derivative also. But we don't need more than 2 conditions. We only need 2 conditions, right? We have 2 unknowns. Great. So let's try to solve this. So this means a is equal to minus b. Okay. So that means e to the power minus jkd minus e to the power plus jkd must be 0. Now what is this, guys? This is nothing but 2 into I into sine kd, right? So that's what it is. This must be equal to 0, which implies that sine of k into d must be 0. A is not 0. Okay, we only know, see, a is equal to minus b, that much. That's all I know. Okay. So I know that in general, if a is equal to b, my wave function phi of x must be of the form some a. I cannot reduce it any further, right? So it's a into 2i into sine kx. This much I know. Okay, because e minus jkx is nothing but cos kx plus j sine x. Cos kx plus j sine x, sine kx. This is cos kx minus. So you do that. A into minus sign can be absorbed in a. So it is nothing, and 2 also can be absorbed in a. So it is going to be, finally, I know that my wave function is something of the form a into sine of kx. Okay, my wave function is the form a into sine of kx, and at x equal to d it should be 0, right? So what does this imply? This implies k, what is my k? K is nothing but root 2 me by h bar square, right? Into d must be equal to what? Sine kd is 0. That means k into d must be what? Should be n times pi, where n is not 0. Okay, can never be 0. N is 1, 2, 3, 4, 5. So why is it not 0? I'll show you why is it not 0. So because if k itself is 0, if k itself is 0, then the wave function will vanish. Remember, wave is not outside. Wave is if vanishes inside also, that means the wave is not there at all, right? So that's not possible. So anyway, I'll come to that a little bit later. I hope everything mathematics is clear until this part, right? So condition is that k into d must be 0. That means k into d must be n times pi, where n can be n can be plus or minus 1, plus or minus 2. It can be 0 also. If I say sine kd should be 0, then the condition is kd should be n pi. N is, yeah. So d is k is n pi by d. Where until now we don't know anything, we say it can be 0 also, can be plus or minus 1 also. Okay, all these conditions are possible. So now we have a good idea about the wave function. We know it looks something like this: a into sine, instead of k, I know it should be n pi by d into x. Now let us think about all these possibilities: 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Okay, what if n is 0? If n is 0, your phi x will become identically 0. That's bad, because remember my well, right? I know that wave cannot be here or here because these are infinite walls. Now you're telling me wave cannot be here also. Then where is the wave? It's completely gone, right? That cannot be. That means wave cannot be in that. So this is why n equal to 0 is not a solution. Is not a solution. Okay, right. Plus and minus 1, right? Now let me tell about that. If plus 1, then I'll get something like n pi by d into x. If it is minus 1, I get a into sine of pi by dx with a minus sign here. Remember, see, physically observable thing is a mod of phi. Okay. So both will have the same mod only. So n equal to plus 1 and minus 1 are indistinguishable from a probability point of view. And thus, they are identical wave functions, the identical solutions. Okay. So we know that n can be only go from 1, 2, 3 to infinity. Great. So we know that my k into d, this k, right? This can only take the values n pi by d, where n is 1, 2, 3, 4, and so on. But what is k? K is nothing but root 2me by h bar squared. Then can only take the value n pi d. And so I can say that E will take the value n squared pi squared by d squared to h bar squared by 2 mass. So E can only take discrete values. See, we got this, right? This n squared pi squared h bar squared by 2m d squared. So what are the possible eigenvalues? It is E1, E2, E3, E infinity, where E1 is given by pi squared h bar squared by 2md squared. N is 1, right? So we can say that energy values of the electron En is nothing but n squared times E1, where E1 is pi squared h squared by 2m d squared. Let us look at this. Let us look at this. This part is clear to you. It's just n squared times, no problem. What is this physically telling, right? What is the only parameter here? There is the mass of the electron. Pi a h, all these are physical constants, right? They're numerical constants, not physical. Mass of the electron, excuse me, and d is the width of the well. D is the size of the well. And what is it telling me? What it's telling me is that the lowest possible energy, this is called the ground state energy. Ground state energy. The lowest possible energy, the ground state energy. Let me see where we are doing on time here. Sorry, guys. Yeah. Ground state energy is inversely proportional to the mass of the electron, mass of the particle. So my particle has very high mass. That means E1 will tend to 0. That means E2 will also tend to 0. That means E2 minus E1 will tend to 0 if mass is very high. Okay. So, for example, I put U. Okay, maybe I'll take somebody else today. Sorry, Prankush, I'll take somebody else. Maybe Priyesh, right? I put this guy inside the infinite potential well. Can he only possess discrete values? Not really. The difference between E1 and E2 is negligible, will become negligible. So he can have continuous values of energy and his ground state energy will be 0. So he can sit quietly, but not the electron. Unfortunately for the electron, its mass is very low. So its ground state energy is not 0. It cannot sit quiet, even if it's at 0 Kelvin. There's no temperature here, right? Just by quantum mechanics, it cannot be idle. Okay, if it is sitting idle at the center of the wall, then it has 0 momentum. That's not possible. It has zero position uncertainty, which means its momentum uncertainty is infinite, right? So that it doesn't allow that. Okay, I hope this is clear. So the higher the mass, lesser the quantum effects for a given quantum well size. And the second thing is, the wider the quantum well, D gets larger and larger and larger. You have wider and wider quantum wells. Once again, less quantum effects are seen. Okay, these are very important things. Why? Because, see, if I have an electronic device, and let me make a device, right? Let's think of a MOSFET, right? So this is your channel, and this is your oxide, and this is your metal gate. This is like a well only, na? See, it's like a well, right? In this direction, it's a well. Okay. So whatever insights we have gained now about you can already apply to this system, right? What do we discover? We discover that if the oxide thickness is small, then only the quantum confinement effects are going to come. Then only the quantum mechanical effects. Otherwise, the oxide is very large, no problem, right? No problem. It will behave classically. Okay, no problem, right? Second thing is the effective mass of your carrier. If the effective mass is quite small, and so in some systems, and depending on a material, okay, so if I take in silicon, for example, or I'm taking some other semiconductor, gallium arsenide, the effective mass of the carriers is going to change. So, for example, in gallium arsenide, the effective mass is quite low. Okay, so in gallium arsenide, people were able to observe quantum effects at much earlier than they observed in silicon. Silicon effective mass is quite large compared to gallium arsenide. So, in 1980s only, already people were doing quantum experiments with gallium arsenide based electronic devices, but not with silicon. No? Silicon only came later on. Now you can understand why, right? It's all there in this equation. Effective mass of the carriers and the size of the well. The other thing, immediately we know that the moment your device starts becoming smaller and smaller, this is your D, right? Quantum effects start dominating. Okay, so that is your that is the power of the very simple equation, right? I mean, the story is not yet over, right? There's other things we need to discover about this. For now, let us just finalize what we have discovered. If I have a potential well of span D, I know that the wave function is going to look like this. It's going to be 0 for x less than a. It's going to be 0x less than or equal to a, greater than or equal to d. It's going to be 0 here as well. Here it's going to be a times sine n pi by dx. N pi d by n, sorry, n pi x by d. Now, I think there's one last thing let me do before finishing. Let us find out this A. Okay, it's bothering us, right? How do we find out that A? Well, we know that the electron is located between 0 and D. So what is the total probability of locating the electron between 0 and D? Must be 1, right? So I do A squared sine squared n pi by x, n pi d by x dx, and this will give us the value of A. Okay, I'll leave it as an exercise for you. So it will be A squared equal to this is 1 here, and inside I have x equal to 0 to d sine squared of, let's do in general, I guess we can do that also, n pi d dx, right? So if you do it, I think it will come out to be 1 by root 2 pi a or something like that. Okay, this is how it will come by. You can please do an exact version. It will come some, there will be n also, I think. There may be n also. Yeah, so it will come something like that, right? So it is that is what I mean by doing normalization. Okay, so that's done. But more importantly is all the other things that we have discovered. So A will be determined by that, and n can only go from 1, 2, 3, 4, and so on. This n is called the quantum number for the infinite well problem. Okay, so n is your quantum number. So here we have not considered the spin of the electron. So if spin is also considered, what will happen is that in the first ground state, there will be upspin, downspin electrons. Second state, here, upspin, downspin, and so on. Okay, n is called the quantum number for this problem. So if this is a one-dimensional well, right? So we got only one quantum number. If I was going to consider a two-dimensional well, I would get two quantum numbers. One for x dimension, one. If I would consider quantum well in all three dimensions, I'm going to get three numbers. Okay. So remember, if you have done chemistry in your IIT, JEE, and so on, orbitals, you have N, L, M, and S, right? So these three comes from the three spatial dimensions. This comes from the spin dimension. So I hope the concept of quantum numbers is clear. That's all there is to quantum number concept. It is all coming from any confined quantum state is always going to have only a discrete number of energy eigenstates. Could be countably infinite, but they're going to be discrete, right? Remember, there's a difference between free space. Energy could be any value. Whenever it's confined, see, free space was spread everywhere, right? It's delocalized. But what is a confined? It's localized. Anytime I localize any particle, because it has to satisfy the boundary conditions, immediately it can only take a finite number of energy eigenstates. This is what we know as quantum. This is the key to the word quantum in quantum mechanics. Energy is quantized. So we say that energy is quantized. Energy is quantized. This is where the quantum comes in. Okay. And now we considered an infinite potential well in one dimension. But the insights from this is very vast. Okay. You can, if you really understand the infinite potential well, you can understand all of chemistry, because all of chemistry is nothing but chemistry is nothing but an atom. Atom is a three-dimensional potential world, right? So any insights that we get about solving Schrodinger's equation in an one-dimensional infinite potential is so powerful that this will allow you, if you really sit down and think about it, it will allow you to understand kind of all of chemistry. Okay, that is why this is a very powerful problem. Okay, so I think I'm taking up more of your time. It's already 6:30, so I'll stop here, and we will continue in the next class. Yes, sir.
Yeah. So what is the boundary value for mass and distance for energy is like a quantized? Like energy state is a discrete energy state.
नहीं, आपका क्वेश्चन समझ में नहीं आ रहा है मुझे.
So what is the boundary value for mass? Yeah, here
Mass
is
is a mass का boundary value कैसे होता है? Mass is a fixed parameter, ना?
no, sir. My question is, sir, when here mass is very less and d is distance is also less, then we get the energy state is like a discrete energy state.
हाँ.
Then what is the boundary value for this distance? So after that we get like a continuous energy state.
Okay. Okay. मैं आप क्वेश्चन मुझे समझ गया ना. तो actually, see, there is the energy will always be quantized on, no matter what value of m and d you take, right? It is just that the quantization will start to appear more and more continuous, because E1 minus E2 will become less and less. It will not exactly go to zero. It will tend to zero. समझ गए?
Yeah, yes, sir.
वही क्वेश्चन था ना आपका?
Yes, sir.
Okay. Any other question?
No, sir.
Anybody else? Any question? Okay, if not, we'll close. I hope this material is being clear to you. Please interrupt if any of this is not clear to you. And also please interrupt, and the physics is, see, mathematics is not very hard here. Okay, so मतलब मैं भी कर रहा हूँ, and I am like, very, very not very bright, right? So obviously, so if I can do this mathematics, then all this algebra, you should say that, okay, यार ये भी कर रहा है, मैं भी आराम से कर सकता हूँ. That is not the hard part here at all. ठीक है? The hard part is really every equation that you're writing, your mind should clearly grasp the physics. Okay, what is it that we are physically trying to say about the system? For example, this n is not zero, right? This is mathematically, this is kind of trivial, but physical implications of this are very profound. So ground state energy will never be equal to zero. That implications of that are very profound, right? So please do think about it, and if you have any questions, do ask about it. If you don't have any questions, that makes me worried कि भाई कैसे हो सकता है, right? So the math is not difficult. The conceptual understanding is incredibly difficult. The reason is that we don't see anything like this in our daily lives at all, right? So please do think about that, and do ask me if you have any questions. So with that, I am going to stop.
Sir?
Yes, ma'am.
Sir, so from next term, we are going to have online classes or offline?
कौन था यहाँ पे? कोई somebody was ill, right? Who was that? Is she here today?
Me, sir, me.
हाँ
Sir,
मैम,
I'm
आप ठीक हो गए?
okay.
Huh?
Sir, from Friday onwards, I think I'm okay with the majority.
ठीक है, तो what do you want physical classes, folks? Any thoughts? Anybody objecting to physical classes? Like offline, मतलब in-person classes? Anybody objecting? Okay, I guess most people would keep me at arm's distance, but apparently you don't want to do that. So great. If that is the case, Monica, well, let's do physical from Friday.
Okay, sir.
Monica?
Yes, sir.
हाँ मैम, लेकिन अपना टाइम चेंज हो गया ना, उसका थोड़ा देखना पड़ेगा, ठीक है? तो फ्राइडे कौन सा अपना 204 है ना, वहां मिलते हैं, and based on whether that's room available, we'll take it. If not, we'll have to change. Okay, but well, let's meet at 204, 7204.
Okay, sir.